Let's continue with our lecture series on design of reinforced concrete structures, starting with the discussion of flanged beams today. So in our previous lectures, when we discussed the design of whether singly reinforced or doubly reinforced beams, we were actually discussing the design of isolated beams. For example, if you can visualize some RCC columns, for example, we have 4 RCC columns here that is supporting a water tank at the very top. And you can say that these RCC columns are supported by beams at different levels. So if you visualize this structure, then the beams that are constructed here, these are the isolated beams. That means there are only beams here and there is no slab here. There is no monolithic construction of beam with any other frame element here. However, if you look at real structures, then often the beams and the slab are cast monolithically. The reinforced concrete slabs that are used in floor systems, the roofs of our buildings and our deck systems are mostly cast monolithic from the bottom of the beam to the top of the slab. And as these beams and slab are cast monolithically, then they act as a single element and act compositely. If you look at this diagram here, this diagram shows a slab system which distributes the load that is coming onto it in only two directions, that is, in these two directions here. This type of slab is generally known as one-way slab. We will discuss about it during our design of slab lectures. But for now, just imagine that all of the load that is coming onto this slab is distributed in these two directions, and those loads finally reach the longitudinal beams that you can see in this diagram here. So the loads that is distributed by this slab are resisted by these longitudinal beams here. You can see one beam is at the edge of this slab, whereas another beam is at the somewhat middle portion, not the edge but towards the middle of the slab. And if you see the shaded diagram here, one that is being made by this end beam and the slab, and another that is being made by this longitudinal beam here and the slab, you can see some shapes are being made here, and these shapes are shaded here. This is our flanged beams. We call these flanged beams because this top surface that you see here, in which the beam intersects with the slab, this is known as the flange of the beam, whereas the bottom portion is known as the wave of the beam. So these are the flanged beams here. This is a T-beam and this is a L-beam, or you may also call an inverted L-beam. So these are our flanged beams that are made due to the monolithic casting of beams and slab. So the figure on the right hand side here shows an exaggerated view of the deflection of such flanged beams, or let's say T-beam here. This is only an exaggerated view. You can see some cracks also here. So if we suppose that this slab is part of a continuous system, let's say that this is a continuous slab with continuous beams here, and we have support here in the position of these two beams. So when you draw the bending moment diagram of this slab, if you remember, you generally draw the bending moment of this kind here. So this is an approximate bending moment of this continuous slab. So at the mid-span of this slab here, there is a positive bending moment, whereas at the supports here, we have negative bending moment. So the positive bending moment means that if we suppose that this is the section of our beam here, then we have tension at the bottom surface and compression at the top surface. So but in this diagram here, I think an opposite sense of bending moment has been taken here. So the positive bending moment is expressed. So let me draw it with another color here. The positive bending moment has been taken to be hugging moment. So if we take the opposite sense to be positive, we can draw our bending moment in this way. So in this case, the mid-span will have positive moment, and for this positive moment, what we have assumed is that the top fibers of this beam are in tension, whereas the bottom fibers are in compression here. So if you look at the diagrams of our T-beams for the supports, that means this diagram and this diagram here. The shaded portion represents the compressive zone. Since at the supports we have negative bending moment, and according to the sense of bending moment that we are assuming here, this negative bending moment means that our top fibers of the beam are in compression, whereas the bottom are in tension. So this shaded portion represents the compression zone of this T-beam for both these diagrams, for diagram number B and also for diagram number D. Whereas for the mid-span, where we have the positive bending moment, this bottom section or this bottom part of the T-beam is the compression zone here, and this is represented by this shaded diagram here. So it says negative moment here, so whatever sense you assume that is either positive or negative, that sense or the position or the location of positive and negative bending moment differs from the support and the mid-span. This figure is only trying to demonstrate that here. So before proceeding with the analysis and design of the flanged beams, we have to first learn how to determine the effective width of our flanges or effective width of our beams here. So let me draw a certain section of flanged beams here. So here I have shown the sectional view in which we have two spans here. One is this span and another is this span here. So the end beams forms a L beam here. That is, the discontinuous edge of the slab forms L beam, whereas the continuous end of the slab forms our T beam. So the distribution of stress that is coming onto this T beam helps us to determine the span or the effective span of this T beam here. So what generally happens is that if you look at the stress distribution, at the support, there are no longitudinal compressive stresses in the flange. That means, let me draw a diagram here. So let's say that I have divided this beam and the slab portion here, and this is the support point, this end, whereas this is the mid span of our beam. This is towards the mid span. So what generally happens is that in this support area here, in this support edges, there are no longitudinal compressive stresses in the flange. But at mid span, the flange is subjected to full compression. That is, the full width of this flange is stressed in compression here. So if you look at the distribution of compressive stresses in this flange here, this is somewhat of this nature. That means the full width of the flange is subjected to compression. And this compressive force is generally higher near to this wave of the beam as compared to these farther edges. Let me repeat that again. This portion of our flange which is closest to the wave, these are subjected to higher compressive stresses than the portion farther away from this wave. So let me erase this and let me come to the diagram that we have here. So you can see that this diagram in black line represents the actual stress distribution. These are the longitudinal compressive stresses, and these stresses are higher nearer to the wave of the beam as compared to the farther edges. So what we can do is we can determine an effective width of the beam such that the distribution of these compressive stresses can be taken to be approximately equal along the width as represented by this rectangle here. And this effective width can be determined from the clause 23.1.2 as given in IS 456-2000. So there are different formula for finding the effective width of both isolated beams and non-isolated beams, and that also for both T beams and L beams. For example, for T beams, the effective width is given by this formula here. L0 by 6 plus BW plus 6 times DF, where L0 is the effective length of your beam, BW is the breadth of the wave is represented here, and DF is the thickness or the depth of your flange. That means this dimension here. Similarly, for L beams, the effective width is given as this formula, and for isolated beams, the effective width are given by this formula here for T beam and for L beam. For T beam, it is L0 over L0 by B plus 4 plus BW, and for L beams, the formula is the same except that we add a 0.5 here. So BF is the effective width, L0 is the distance between points of zero moments in the beam. That means this is the distance between the points of zero moments. Points of zero moments, you also can call this as points of contraflexure. And this distance between the points of contraflexure is also the effective span of your beam. BW is the breadth of the wave, DF is the thickness of flange, and B is the actual width of the flange. So these are the formula that help you to determine the effective width of flange. Now after determining the effective width of flange, you can go to the analysis of your beams, but before going to analysis, there are some conditions or there are some cases that you must know. So let's see here. The neutral axis of a flanged beam may be either in the flange or in the wave depending on the various physical dimensions of your beam. For example, effective width of both wave and flange, thickness of flange, and also effective depth of flanged beam, that is total D. So if this is your T beam here, your neutral axis may either lie within this flange portion, your neutral axis may lie at the boundary of this flange and wave, or your neutral axis may lie at the wave section here. So these different situations may be possible. The flanged beam may be considered as a rectangular beam of width BF and effective width D if the neutral axis is in the flange as the concrete in tension is ignored. That means, let me draw another diagram here. And let us say that now the width of this T beam is its effective width BF. Now if you say that your neutral axis lie within this flange here, this is your neutral axis, then what this means is that this above portion of your T beam, that means the portion of your concrete above this neutral axis, resists the compressive forces. That means this area of concrete is responsible for resisting the compressive stresses, and the remaining area of your beam that is below this neutral axis, you can ignore this area totally because we do not consider the tension carrying capacity of our concrete. So if you can ignore this concrete area that is below the neutral axis, then you may say that this T-beam is a rectangular beam of width BF and effective depth D. So although your tension reinforcement may be here and this is the effective depth of your beam, since you do not need to consider the concrete below the neutral axis, your effective section becomes a rectangular section of width BF, that is the effective width of flange, and D, that is effective depth. But if your neutral axis is somewhere in this wave, for example, if your neutral axis is wave here, now your compressive forces are resisted by both the area of concrete in your flange portion and also some part of concrete in your wave portion. You can ignore the concrete below, but now you cannot assume it effectively as a rectangle of width BF and D that you did when the neutral axis was in the flange portion, because now the concrete compressive forces are also resisted by the concrete in the wave zone here. So before analyzing your T-beams or L-beams, what we have to find is, it is important to find the depth H of the beam where the strain is 0.002. So if you remember our assumptions of flexural analysis, what we discussed is that if you look at the stress strain curve of your concrete, then it is both parabolic and rectangular. It is parabolic from a strain level of 0 to a strain level of 0.002, and it is a straight line from 0.002 to the portion of 0.0035, and 0.0035 is the point of your failure. So you have to find the depth of the beam, and that depth is represented as H, where the strain is 0.002. So if this depth H is also represented here in figure, you can see here, this is the level where the strain value is 0.002, and this level is at a distance of H from your epsilon c equals to 0.0035. So if it is located in the wave, the whole of flange will be under the constant stress level of 0.446 FCK. So if this H is somewhere in your wave portion, for example here, let us assume that this is the depth H where the strain level is 0.002. So we know that from strain level of 002 to 0035, that means above this value we have a constant stress level, and this constant stress level is given by 0.446 FCK. So if this H lies in the wave zone here, then you can say that this whole of flange is under a constant compressive stress of 0.446 FCK, whereas if it is located within the flange itself, only a part of the slab will have the constant stress of 0.446. That means if your H lies somewhere here, only this upper part of the flange is under a constant compressive stress of 0.446, and the stress now is different for this below part here. So these are some things that you should remember for the analysis of flanged beam, and we will use these conditions when we develop 4 different cases for the analysis of our flanged beams. So how do you determine that depth of strain H? So there are 2 different ways to determine the depth. One is from the strain diagram. If you remember your strain diagram, we had something like this here. So here we have the maximum compressive strain of 0.0035. Let's say that at this level we have the strain of 0.002, which is at a distance of H, and this is the depth of our neutral axis, which is at a distance of Xc. Now if you consider the similar triangle property, then you can write this as 0.002 divided by 0.0035 is equal to xu minus h. That means this portion here, xu minus h divided by xu. Rearranging this equation, you will get the value of h by xu as 3 by 7, which is equal to 0.43. First, let us consider that xu is equal to xu max. That means we have a balanced section here. And we know that we have various relationships for xu max that relates this value with the value of the effective depth for different grades of steel. And if you use those values for different grades of steel, you will get the value of h as 0.227D for Fe250 grade steel, 0.205D for Fe415 grade steel, and 0.197 for Fe500 grade steel. For that, we have to develop the relationship between xu max and D, which we have already discussed, and substitute the value of xu max here. Instead of xu, substitute the value of xu max, which is in terms of D. So if you can see here, all of these values for different grades of steel are very nearly equal to 0.2D. So in general, we can say that H by D ratio is equal to 0.2. You may also derive this relation from the values of strengths of concrete and steel. You can use this relation also, epsilon St over epsilon C equals D minus xu over xu. This will give you the relation of D by xu as epsilon St plus epsilon C over epsilon C. Now substitute the value of epsilon St and epsilon C here, and then you can get the value of H by D. So you may adopt this method also, or you may go with this similar triangle method also. So we got here finally H by D equals to 0.2. So let's say what is here, the maximum value of H may be Df at the bottom of the flange, where the strain will be 0.002 if Df by D equals 0.002. For this case, the thickness of the flange may be considered small. If Df by D does not exceed 0.2, the position of the fiber of 0.002 strain will be in the wave, and the entire flange will be under a constant compressive stress of 0.446 FCK. So what it is trying to tell us is that the maximum value of H may be Df. So let's see here. We have got here H by D is equal to 0.2. So we can say that H equals to 0.2 D. But we know that what happens if the maximum value of H is equal to Df. So in that case, if you draw a T-beam here, we know that this is the depth of flange. So if the maximum value of H max is Df, that means this line coincides here. Let me draw it with another. So this is the line which coincides with the value of Df as measured from the top here. So this is also the value of H. If you consider that the value of H max, or the maximum value of H, is equals to Df, you can say that this is the line where the strain in the fibers are 0.002. So above this line here, all of this concrete will be in a constant compressive stress of 0.446 FCK. So this is what it is trying to tell you. If Df by D does not exceed 0.2, the position of the fiber of 0.002 strain will be in the wave, and the entire flange will be under a constant compressive stress of 0.446 FCK. Now, increase the value of H here. In second case, let us say that now our depth of H lies at this distance here. So this is our H. Even in this second case, again the value of the stress in this flange will be constant of 0.446 FCK. In the third case, even when your H lies here, then the value remains constant. But if the value of H is decreased from here, for example, you say that this is the depth of H here, then only this part of the flange will be under a constant compressive stress, and the stress will be different for this lower part here. So if dF is greater than 0.2, the position of the fiber of 0.002 strain will be in the flange. For this case, only a part of the slab will have the constant stress of 0.446 FCK, whereas the strain will be more than 0.002. This is the same thing that we discussed in our previous slide here. So based on this concept, we have 4 different cases for the analysis of flanged beams. The first case is that the neutral axis is in the wave. That means your neutral axis is somewhere here. The second case is the neutral axis is in the, this is neutral axis is in the flange, so your neutral axis will be here, not here. And the remaining 3 cases are where the neutral axis is in the wave, but the second case is the section is balanced. The third case is the section is under reinforced, and the last case is where the section is over reinforced. So the section is balanced means that the value of the depth of the neutral axis is greater than the value of dF. The case of under reinforced means that the maximum value of xu is greater than the value of xu, and the value of xu is greater than the value of dF. So that means if this is your neutral axis, then this is the value of xu, but the value of xu max will be somewhere here below this xu. And finally, the last case is where the neutral axis is in the wave and the section is over reinforced. That means if this is your maximum depth of neutral axis, then your actual depth lies somewhere here, xu. So in our next lecture, we will start with the first case, and then we will see all the 4 cases and the formulae that will be employed in the analysis of flanged beams for all these 4 cases. So this brings us to the end of today's lecture here. We'll meet again soon in our next lecture when we continue with the analysis of flanged beams. Till then, stay safe and thank you.